Welcome everybody.
Recording now.
Lovely, thank you, Stuart. So welcome everyone to our second Thought Leadership series or programme with the CSEE. Our relationship, BT's relationship with Essex, is our longest running relationship and goes back to the earliest days of Adastral Park. So many people, BT people, are alumni of the university, and we've currently got 3 visiting professors, including our MD of Applied Research, Professor Tim Whitley. So we also work with the business school, and we've got a strong collaboration with the CSEE, where we've delivered real impact over the years. So I'd like to hand over to Stuart, who's our central point of contact at the university, and we've pulled the series together.
Thanks for that nice introduction, Sarah. Well, it's not my show today, it's Zilong's, but he asked me to introduce him, which is my privilege. He joined our department in December 2019, and I'm pleased to say since that moment, he's been extremely active. I won't summarise his whole profile, but an example is he's a senior member of the IEEE, associate editor of IEEE Wireless Communications Letters, IEEE Access, Frontiers in Communications Network, etc. He's also been general co-chair in 2021 this year of the International Workshop in Signal Design and its applications in communication. And while doing all those tasks, he's managed to produce over 100 peer-reviewed journal and conference papers with the outstanding tally of 40 IEEE transactions papers. So he's very well qualified to give his talk today, which is entitled 6G for Future V2X Communications. Over to Zilong. Thank you.
Thank you very much, Professor Stu. Thanks very much for your very warm introduction, and also thanks very much to Sarah and the colleagues from BT for organizing such a wonderful event. Let me share my full screen. Can you see my screen now?
Yes.
Full screen. Okay. Okay. The title of my today's talk is 6G for the future V2X communication. So this talk will be divided into 4 sections, and in the first 2 sections, you will feel that they are relatively easy to pick up, and I will share our first why V2X communication is a must, and secondly, I will share with you a lot of enabling technology challenges and opportunity for the 6G enabled V2X communication, and this section will be and this section is related to our submitted paper, which you can actually find such a paper through the internet in the archive now. And in the third section, I will share with you our novel results on the code domain normal. So I have been working on code domain normal since 3 years ago. I have moved to UK, and since 2 years ago, I have started to work on the joint communication and sensing, and this will be based on another of our submitted paper, which is shown here. Okay, let me now from this table, we can see the mobile evolution from the 1G to 5G. And 1G actually was launched in 1981 with a transmission rate just 2 kilobyte per second. And with all these years, we can see from 1G all the way to the 5G. Since 2020, 5G has been rolling out across the world, including UK, with the maximum transmission rate of 20 gigabyte per second. So with all this, we can see that in terms of our mobile phone, the function are becoming more and more complicated. And so the question here is that what does 5G mean to us compared to 4G? Does this simply mean that 5G simply means a higher transmission rate? Then we are able to do a better video streaming compared to the 4G. For us to understand this, we need to first introduce you many vertical industries in the 5G and beyond mobile networks. And in this picture, we can see that we have the 5G and beyond communication network will be used to transform the factories of the future to energy, e-health, meeting and entertainment. But the question here is that among numerous vertical industry, which one is the most promising, which can shape the major revenue of the 5G and beyond communication networks? So what we believe is that the automotive vertical industry is the one. And the vision is that the collectivity will be at the heart of the next generation vehicle. And according to a very recent prediction from Jabil, by 2025, 88% of all new cars will be equipped with telematics. And in UK, we have a dedicated organization to study the impact of a collected autonomous vehicle. And according to their prediction, by 2035, the UK CAV industry will be worth about 62 billion pounds, which is equivalent to about 6% of the global market. So with the collected vehicle, higher levels of automation are possible and expected, and this will lead us to the significantly improved safety and the traffic efficiency. And in terms of the traffic efficiency, this also implies the less travel time, reduce the traffic jam, the reduce the traffic congestion, and the improved the less air pollution, and then ultimately the improved safety and traffic efficiency will lead us to the fully autonomous vehicle. So essentially, collectivity will be the foundation of the next of the future autonomous vehicle. Just imagine how excited it is that in a few years' time we are able to go to anywhere through our driverless car. For us to realize such a vision, it is essential for the vehicle to constantly exchange the message with its surrounding environment, and also such a vehicle should be able to constantly sense its surrounding environment for the improved situational awareness. So the question at the central is that how we can ensure that the driving is always super safe and pleasant. In order for us to do so, we need to have a highly scalable vehicle to everything communication network. With such a network, every vehicle is able to talk to its surrounding vehicle, which is called V2V, and every vehicle is also able to talk to its surrounding infrastructure, to the network, and to the pedestrian. But however, there are numerous challenges for us to solve. For example, how we are able to ensure that some mission critical message can be timely and correctly delivered, and how we are able to support quality data services in high mobility channel, where in this case the receiver needs to deal with the increased amount of the interference imposed by the Doppler, and how we are able to support the massive collectivity with a highly congested spectrum. So before I move further, I would like to give you a very brief introduction on the evolution of the V2X communication. The current battle of V2X communication is mainly between DSRC and cellular V2X. Here, DSRC refers to the short range communication, where the first generation DSRC was launched in July 2010, which is characterized by the standard 11P. And then in 2019, they have released another standard, which is called 11BD. This is regarded as the second generation DSRC. The major advantage of the DSRC is that it assists the DSRC does not need to use any cellular infrastructure, so it is relatively easy to deploy. And so because of this, in the past decade, DSRC has been drastically pushed by many European countries and companies such as Volkswagen, Toyota. But one of the issues for the DSRC is that it may not work very well over a very dense and high mobility environment, and also using the DSRC may lead to a very long communication latency. Okay, so and for us to achieve the improved situational awareness, even each car is equipped with radar, camera, LiDAR, and also with the DSRC, which with the maximum communication coverage about 1 kilometer range. So it is ideal that we are able to have a long range sensor. So for this, there are also many companies. They tend to use the standard V2X communication, and so far there are two major forces which are drastically pushing this standard V2X, mainly China and the USA. So those many are driven by Huawei and Qualcomm. So with this, it is also essential for us to introduce about the Kpi jump from the 5G to 6G. And in the 5G era, we all know that 5G has needs to support these three major use cases. But actually, at the initial stage of 5G, it seems that we mainly focus on the first one, which is called EMBB. So my vision is that it may still take quite a few years for us to see the massive machine type communication and URLC. But actually, over the world, the 6G research has attracted a tremendous research attention. So here is one paper published last year. If we look at the some KPI here, so for example, the peak data rate, and we can see that from the 5G to 6G, this will be jumped from 20 gigabyte per second to 1,000 gigabyte per second. And also in terms of the collection density, in the 5G era, we are supposed to support 10 to the power minus 10 to the power 6 devices per kilometer square, whereas at the 6G era, we need to support 10 to the power 7. And in terms of the mobility, and we can see that 5G needs to support the maximum mobility of 500 kilometer per hour. The main challenge here is that the higher of the mobility, we need to the receiver need to deal with the increased interference from the Doppler. But however, in the 6G, we can see that we need to deal with 1,000 kilometer per hour. In addition to this, in order for us to support the fully autonomous driving, we can see that here in terms of there is another KPI which is called the position accuracy, and for 6G we need to support the position accuracy down to 0.11 meter. So how we are able to design a V2X communication system with the aid of satellite being forming whatever, such that we are able to increase the position accuracy. This is also a very a major research problem. And in this paper, we have summarized many and typical use cases in the 6G V2X communication. And if you look at the here, we can, with the 6G V2X, each vehicle is able to talk to the drone, talk to the satellite, and we are able to use the beamforming and techniques to improve the localization, and also we have the platooning, which is shown here, and we have the real-time mapping, which is shown here. All right, and also in this paper we have summarized many evolving technology, and so for some technology I will introduce it later. For example, LoMa I will introduce in the section 3, but in the section 4 I will introduce about the joint sensing and communication. But in addition to this, the trend is that the integration will not only between communication and sensing, but it will also between the communication and localization and communication and control. Besides this, in order for us to achieve a highly secure V2X communication, nowadays there have been a lot of research considering the quantum computing and the blockchain. And so another revolutionary technology is also called the programmable V2X environment, with the aid of intelligent reflective surfaces. So if you are familiar with the Shannon capacity, and in the traditional communication system design, basically the one channel is actually regarded as a passive entity. So that means that we can do something for the transmitter, we can do something for the receiver, but there is a very little thing that we can manipulate for the wireless channel. But with this emerging intelligent reflective surfaces, we are able to create a smart radio environment. And recently, it has been shown that based on such intelligent reflective surfaces, we are able to customize the carrier phase rotation, carrier frequency, even the polarization. So this will allow us to mitigate the multipath propagation as well as the Doppler effect. But also we have the machine learning enabled V2X communication. There has been many papers, and in terms of the very high rate communication, and there has been a lot of research concerning about the terahertz communication. Now, one of the major challenge in the V2X communication is how we're able to support the massive and ubiquitous V2X communication. So for that, NORMA is emerges as a major technique to deal with massive collectivity in the V2X communication. And roughly speaking, there are two types of NORMA. One is called the power domain in NORMA, where two or more users share the same time and frequency resources, and by sharing, but what we do is at the transmitter side, we assign different user with different power. So for example, in this case, user 2 will be giving larger amount of power. So at the receiver side, whenever we want to decode the transmit signal of user 1, so we first decode out the user 2's signal first, and then we subtract out the user 2 signal from the received signal at user 1, followed by the decoding of user 1. And in addition to this, we also have the code domain and norma. And so the code domain norma has a strong connection with the traditional CDMA system. So the main idea is that each user will be giving a sequence or a code book. Okay, so because this this is called the code domain norma, and depending on the code book has any sparsity or not, we have the sparse code multiple access, and also the dense code multiple access. Sparse or dense, which is better. And in this paper, we have compared these two code domain techniques, and I will show you some more results in the coming slides. So before I move further, I need to spend one slide to introduce the so-called low density signature CDMA. So this paper was published in 2008. You can see that here is the transmitter receiver structure. You can see, if you are familiar with the CDMA system, you can see that this is very similar to the traditional CDMA system. Basically, we first do the modulation followed by the sequence spreading. Okay, but the only difference is that here, instead of the traditional CDMA system, use a very dense sequence. Here, every user will be giving a sparse sequence. So in this case, this is called the low density signature. Okay, and then at the receiver side, so the receiver will see a linear equation, and then so this y equals to hx plus w, where h is essentially is now a sparse and fat matrix. Since such a matrix is sparse, this will allow us to use the messy use the messy parsing to do the decoding. So essentially, each system can be related to such a factor graph, and then we are able to use the BP decoding to decode such a system. And here I have shown you the example. So essentially, the number of users here is 16. Okay, but whereas the asynchronous length is actually 12. So we can see that by using such a system, so for the given and time or frequency resources, we are able to support more user in terms of the overloading factor larger than the one, where which cannot be supported by the traditional orthogonal multiple access system. And moving forward, and we have the generalized low density signature, which is called the sparse code multiple access, CMA. So so here I have shown you the example. So essentially here we have the frequency domain is to be divided into multiple blocks, and in this case each block contains 4 subcarrier. So you can see that over this 4th subcarrier, we are able to support 6 users thanks to the sparse codebooks, which where the decoding can be associated with such a factor graph, which enable us to do the decoding using the BP decoding. And here you can see this example how the different codebooks look like. So for example, if for the user 1, if I want to send out bit 11, then I just send out the one. I just need to select one code word from its individual code book, and so on and so forth. And then all the specific code words, they are summed together, and then we got a superimposed code word. But what's the problem of a sparse code multiple access? So here, one of the major issue is that such a system suffer from limited diverse order. If you are familiar with MIMO, and we can see that here we have 4 subcarrier and we have 6 user, and each user will be sending its useful signal over 2 subcarrier only. So in this case, we can conclude that over the relay feeding channel, the maximum diverse order is actually 2. So no matter how we can design our receiver, how we are able to improve our codebook from the transmitter side, the maximum diverse order is limited. So this will become a fundamental bottleneck for us to improve the bit error performance. So last year, we have submitted this paper, and we have instead of using some sparse codebook, we consider some very dense codebook, which is a little bit similar to the traditional CDMA system. But the only difference here is that at the receiver side, instead of using the traditional match filter based receiver, we consider the generalized sphere decoder, which is a classical receiver design in the MIMO system. And here we have compared 2 types of setting. One is the 4x6 normal setting. The other is a 5x10 normal setting. Here 5x10 means that 10 users communicate over 5 subcarrier. Okay, and 4x6 means that 6 users communicate over 4 subcarrier. And we can see that for the hybrid code, so this is essentially a hybrid code, and we can see that where the green curve refers to the block error rate of the DCMA, we can see that we are able to achieve about 3 dB gain, and the same can be said for the 5x10 normal system. So what we have found is that by using such a dense codebook, we are able, so the entire receiver is able to enjoy the full diversity order. So here actually a very interesting future work is that how we can improve such a system which can work in the high mobility channel. This is a very interesting research we have been doing now. So much for the normal. And now let's move to the last session, which is on the joint communication and sensing. And in fact, there are many different names for this JCCS. You can find out in some paper. This is called radar-com, which refers to the fusion of radar and communication. Or there are also some paper which is called ISAC, integration of sensing and communication. And so essentially, the joint communication and sensing refers to a kind of a new system where the communication and the radar sensing are using the same waveform over the same hardware set and using the same frequency band. Okay, and because of this, we are assist both the one waveform is able to serve both the communication and the radar. So this will lead us to the improved spectrum efficiency. And in addition to this, since the communication and the radar can work together and they can help each other. So this will lead us to higher beamforming efficiency, and also since both the communication radar using the same hardware, so this will lead us to reduce the cost, the hardware cost and size. Maybe the most important benefits is that both the communication and the radar sensing, they will kind of they are able to mutually enhance each other. Okay, so it's one example is that if we are able to have such kind of system in our car, so the radar sensing result can be fed to the communication module of such a car, and then if such a radar sensed some very dangerous situation, so based on the communication module. So the communication module is able to broadcast such a message to its surrounding vehicular network. So in this case, we are able to have the mutually enhanced communication and the radar sensing. And roughly speaking, we have four types of joint sensing and communication waveform. For example, there have been some paper using 1180 in the 60 gigahertz or the 11p in the 5.9 gigahertz using the communication waveform for the radar sensing. Or there have been also some paper using try to embed some communication message into the radar sensing waveform. So this is called the radar waveform based. And of course, we are able to just use one waveform, but we can transmit such a communication radar waveform in a different time and slot. Okay, so in this case, we call this as the coordinated signal. So what we are trying to achieve, what we are trying to design is that ideally we can design a kind of dual function waveform, which can have some flexible trade-off between the transmission rate as well as the radar sensing performance. In order for us to do so, in this paper, we have considered the waveform design for the with low PPR reduction for the OFDM based radar com system. This has been submitted to the transaction awareness communication. So here, essentially, we consider a kind of scenario that we actually consider a sub 6 gigahertz, 6 gigahertz scenario where the spectrum is highly congested, fragmented. Okay, so in this case, in order for us to achieve a very good radar sensing performance, ideally we need to have the radar sensing need to be assigned with a large chunk of spectrum. However, this is very difficult, due to the highly congested spectrum. So what we consider is that a large radar sensing spectrum over such a large radar sensing spectrum, and we have several non-contiguous communication bands. Okay, we have many non-contiguous communication bands. So you can see that in this case, for the communication transmission, we have very little to do. But whereas for those band which are reserved for the radar sensing, so we are able to leverage such a kind of a band to optimize the radar, the entire radar waveform in terms of its PPR and also in terms of its autocorrelation function, which plays a very important role for the radar ranging. And here we have so here our main tool is to use the modularization, minimization, optimization method, and we have consider omega here. Omega here essentially refers to the bandwidth ratio, which is reserved for the communication. So that means that when omega equals to 0.2, so among, for example, 100 megahertz frequency band, only 20% is reserved for the wireless communication. So we can see that by using our proposed method, we are able to achieve a very low PPR. So in this case, this is below 4 dB. Probably this is about 3 dB, below 4 dB, and this slightly larger than 4 dB, slightly smaller than 3 dB. And we have also plotted our ambiguity function for such an OFDM based radar waveform. we can see such an ambiguity function here. Such an ambiguity function plays a very important role for the improved radar sensing performance. And here I have given you a comparison by using our proposed waveform as well as by using the traditional OFDM waveform. And in terms of the detection probability, and we can see that we are so we can see the gain here. And here we consider 4 car. We consider 4 car here, 4 car here, and by using our proposed waveform, we are able to achieve about 6 dB gain, compared to the non-optimized Redacom waveform. So that's my presentation, and essentially I have introduced to you about why V2X communication is a must, and what will be the key 6G enabled V2X communication. And I have in order for us to support the massive collectivity in the future V2X communication networks, and I have introduced to you about co-domain norma, and also for us to achieve a highly efficient spectrum for highly efficient V2X communication, I have introduced to you about joint communication and sensing. So that's all my talk. Do you have any questions? Thank you very much.
There are some questions. So G10 Ma to everyone. So would you like to announce your question, and Zilong will answer it for you?
Probably I can announce. Okay, so I got one question from G10 Ma. Thanks for the fruitful presentation. Do you think 5G can be replaced by the Wi-Fi 6 or Wi-Fi 7 in the V2X communication due to its low cost? That's a very good question. Personally, I don't regard a 5G new radio as the same standard as the Wi-Fi 6 or Wi-Fi 7, because if you look at the entire 5G major tactics, because essentially, Wi-Fi is kind of Wi-Fi 6 and Wi-Fi 7 is we may regard this as a kind of evolution from the traditional Wi-Fi standard 11A or moving to 11P, 11BD for the V2X communication, right? But whereas for the 5G, I think due to the for example in the network layer, we can carry out the network slicing, and also for the standard V2X, I think in the release 16, there are also some discussion on how to support the ultra low latency and ultra reliable and low latency communication. And so I don't think all this kind of thing and have been discussed in the Wi-Fi 6 and Wi-Fi 7. So it's so I think it's something still like a kind of it's a little bit like the debate between the DSRC and the standard V2X. Okay, in fact, over the world there are 2 groups of supporter. So some companies, some country, they support the DSRC. They think that the DSRC is cheap, but there are also many countries and with the major forces from China and the USA, they support the standard V2X. Okay, so I hope.
Okay, yeah. Thank you very much. Nigel Kirby has a question.
Okay, yeah, so I see one question from Nigel. Zilong, please can you speak more about how blue light services can be intelligently routed and integrated into a smart city? Sorry, Nigel, in fact, I don't have much research on this blue light surfaces, because of my major research is actually more focused on the physical layer. But very recently I have been doing some research on the visible light communication. So I don't know whether your so-called blue light surfaces refer to this visible light communication. But what we consider here is that how we are able to, but what we consider is that how we are able to design a hybrid VRC and the traditional RF communication system, because the VRC is we are able to use a VRC to support a high rate transmission, but that is a very short range. Okay, because it's just like because using this visible light, you can see that this kind of visible light is very easy to be blockade. Once we have any blockage, then we are not able to have a very long range communication. So still, so my vision is that for the future V2X communication or whatever sort of communication, so there might be a kind of hybrid, communication system.
Yeah. Could I just say that I think Nigel was addressing the police, ambulance, fire and rescue services. So not so much the visible light aspects of being blue, but these emergency vehicles. Could you perhaps address that point, please?
Police, ambulance, fire, and rescue services. Yes, indeed. I mean, so you can see that largely I have mentioned in the beginning that collected car, are one of the major advantages is that will lead us to a significantly improve the traffic efficiency. So that means less travel time is because we are able to optimize the travel routine. So and then less traffic jam. So in your case, for example, police, ambulance, and fire rescue services. So certainly, we are able to use the V2X communication to prioritize them, because police, ambulance, they are the first important priority task, right? So this means that when our vehicle moves out, so with the aid of V2X communication, we every vehicle is able to broadcast out such a emergency message to its surrounding vehicle. So I hope that this will help to address all these police, ambulance, fire, rescue services. Thank you, Rob.
Thank you.
Yeah.
Okay. Next question from Felix on your chat line, Zilong.
Yeah. Okay. Thanks for a wonderful provided presentation. Where the application of tactile intellect found a place in the 6G system. Yes, I believe so. Because in fact, in addition to such a tactile intellect, there has also been another very revolutionary technology, which considers the interface between brain and the vehicle. So essentially, the vision is that probably in 10 or 20 years, the time, each passenger is able to control our car with our BCI BCI interface, or using our smartwatch, whatever. So this is so this is in my opinion, and this is a way. And in terms of this tactile intellect, so what I can see is how we can have some very low power design, whereas at the same time we are able to support a very high rate transmission. Those are some technical challenges, in my opinion.
Okay, thank you very much. And there's
Thank
now
you,
a question from Khalid as well on your chat list.
Yeah, thank you for the presentation. Is there any issue with this optimization to consider when a senior V2X is implemented? Yes, I think so. I think, you know, even we have the senior V2X implemented. So you know, very recently I have seen some paper. You know, they have actually considered to use the 5G new radio waveform, okay, to carry out the joint sensing and the communication. If you are interested, I can share with you this the paper to use soon later through the email.
Thank you very much. I've got one question of my own, Zilong, which is a general question.
Yeah.
Could you make some comments about power consumption issues for 6G? I mean, it's going to consume presumably a lot more power than 5G, would you think? Or are there some solutions you can think of?
That's right. That's right. For the power consumption, I think nowadays there have been many research activity concerning about this. One of the major research topic is on the massive MIMO, because one of the thing is that just imagine that you know, if we need to use about you know, hundreds of thousands of the transmit and antenna from the base station. So how we are able to save the power, that is a major issue. So I think for that, one thing is that so in order to address such the low power consumption problem in the massive MIMO, you know, some research consider to use the index modulation or spatial modulation and so on. So yes, indeed, you know, where is that we want to achieve more and more. We want to have a higher rate. We want to have an improved position, and we want to let our communication system work in a high mobility rate. So how we are able to design a greener communication system. I think that definitely is a very interesting research problem moving forward in the 6G.
Okay, so we've got a question here, haven't we, from Steve Aaron?
For Steve,
your chat. Would you like to answer that one? Place
what
of
are
area
your
platforms?
What are your thoughts on the place of a aerial platform as in the V2X? Well, yes, indeed. I mean, if you refer this to some sort of platform like the Jump or yeah, something like Jump aided V2X communication. Certainly, I think this is a very interesting and research, not just in some disaster scenario. So if you are interested in this research, so I can also share with you some more source with you.
Thank you. Last call for any questions. We had a very good round so far. If there aren't any more, perhaps we can draw this session to a close and virtually thank Zilong for his excellent presentation. As we expected, it was most thought protection. I've just seen another question here before we close of Nigel Kirby then.
Yeah. Okay.
Last one.
Question is, do you see potential for AI and machine learning models to be developed that will extend functional and pivot into the other use cases using the V2X technology movement of medical equipment in a hospital? Certainly, Nigel. I mean, so you can see that the V2X communication is essentially deal with the physical layer. You know, how we can deliver you know, one message from one point to another point. Okay, so in a highly efficient way, how we can send out this you know, through the physical layer, one channel, so I always believe that, on top of the V2X communication, there should be a kind of, AI brain to help us, how we can do the resource allocation, and how we can make any decision, particularly for the future autonomous vehicle.
Thank you. So, as I said, we had quite a good round there. I'm thinking that you all know Zilong's address, and if you want to pick up any questions with him, then
yes,
that'll
thank
be
you
fine.
so much. Yes, thank you.
So thank you, Zilong, very much indeed for that wonderful, thought-provoking presentation. Then,
thank you, Stu. Thank you, Stu. It has been my honor. So here you can see my email. Here, if you have some, if you want to have some more interaction and with me, you can write email to me, or if you are more interested in my research profile, you can search my Google page. You can find all my publication and all my previous research project there. Thanks a lot.
Thank you very much, everybody, for coming on this very interesting session. There'll be
Thank
yet
you,
another
Foley.
topic from Essex in the new year. Thank you very much.
Thank you so much.
Goodbye.
Thanks,
Thank you.
everybody.
Thank you. Bye-bye.
So now
Bye-bye.
closing down now, Sarah, is that okay?
That's brilliant. Thank you very much, Stu.
Thank you.
Okay,
Bye.
thank you. Bye-bye. Bye-bye.
Thanks,
Take
Zilong.
care.
Bye. Thank
Have a
you.